So in this lecture, we'll be discussing about the concept of modulus and argument of a complex number, and we'll also be doing a few problems on this topic. So let us consider a complex number z equal to a plus ib. If you have to geometrically represent this, we draw two axes just like our coordinate axis. That x and y axis will be now called as real axis and imaginary axis. So x axis is usually called real axis here, and the y axis is called imaginary axis. And we can also represent a complex number by a point in this plane, and this plane is called as Argand plane. So we usually call this plane as the Argand plane or complex plane or Gaussian plane. If we have to represent any point P here, we join this point with origin. The distance of point from origin is suppose R. Draw the perpendicular like this. So this will be A and this will be B, and you can represent this just like A comma B we represent in coordinate. And from the diagram, you can see that the distance R is root of A square plus B square. This is called modulus of the complex number. The distance of complex number from origin is called as the modulus. So this we call it as modulus of Z. And the angle made by this vector OP with real axis measured in anti-clockwise sense is called argument of the complex number. So this theta is either called as argument of Z or amplitude of Z. Both mean the same. So either you can write ARG of Z, or we can also call it as amplitude of Z. Theta can also be called as amplitude of Z. Amplitude of Z. So we can also write theta is AMP of Z. Both mean the same. Whether we write amplitude or argument is the same. And from the diagram, clearly you can see that because I've chosen this in first quadrant, anyway A and B are positive. But the point can be in some other quadrant where A and B can be negative. So while writing the distance, we'll put a modulus. So from the diagram, you can see that tan theta is mod B by mod A. Tan theta is mod B divided by mod A. And theta is tan inverse of mod of B by A, you can write. So this is called as argument of the complex number. So for the complex number, mod Z is root A square plus B square, and argument Z is tan inverse modulus of B by A. And this is the case where I have chosen the complex number in the first quadrant. And usually the argument in first quadrant should lie between 0 and pi by 2. So this is 0 and pi by 2. So you can just say argument of Z should lie between 0 to pi by 2 for first quadrant. This is when Z lies in first quadrant. Similarly, we'll find out the modulus and argument for different quadrants. Let us find out modulus and argument for different quadrants. So for second quadrant, if you have to make a diagram, so we can just draw the real and imaginary axis. I'll write RA and IA here, where RA represents real axis, IA represents imaginary axis. If we represent a point P again here in second quadrant, and this is the argument now. So this is the argument, and when you drop a perpendicular like this, so this is mod B and this is mod A. Here when you represent P as A comma B, Z is A plus IB of course, but here A is negative and B is positive. So that is why it is necessary to write modulus while writing the distances. So now if you have to write down the argument of the complex number, so the inside angle is suppose theta, then this angle will be pi minus theta. So argument of Z in this case is pi minus theta. And from the triangle, you know that tan theta is again mod B by mod A. So therefore, this will be pi minus tan inverse mod of B by A. So this is the formula for argument in second quadrant, but modulus still remains the same. That is root of A square plus B square. And usually whenever the complex number is in second quadrant, the argument will lie between pi by 2 and pi. So this is pi by 2. This is pi. So you can say this argument lies between pi by 2 and pi. Pi by 2 less than argument of Z is less than pi for second quadrant. Now, if you choose the same thing in third quadrant, so if you choose it here, this is again the real axis and imaginary axis. So you choose a point P, A comma B, where Z is A plus IB. So here we consider again A negative and B negative. But when you draw perpendicular and write the distances, this is mod B and this is mod A. Suppose this angle is theta. When you have to write down the argument, so usually if it is in third and fourth, we measure in clockwise sense. The reason is argument should lie only between minus pi and pi. So therefore, this is minus pi and this is minus pi by 2 when you measure in clockwise sense. So for third quadrant, your argument should lie between minus pi and minus pi by 2. So when you measure the angle, you measure this angle as the argument. And this is nothing but the total angle is minus pi. minus of, when you write this angle in as theta here, when it is measured in clockwise, you normally write minus theta, minus pi, minus of minus theta, which is minus pi plus theta. So negative sign is attached because you're measuring in clockwise sense. So argument of z in this case will be minus pi plus theta, which is minus pi plus the value of tan theta from the triangle is again mod b by mod a only. So it is still tan inverse mod of b by a. So this is the formula for argument in third quadrant. Similarly, we'll check for fourth quadrant in the same way. So if the complex number is chosen in fourth quadrant, this will be the argument minus theta. So when you drop a perpendicular, again mod b here, we have mod a here. So R is the modulus, which is root of a square plus b square. So modulus will not change for any of these quadrants. Argument is only changing. Argument z is minus theta, and that is minus tan inverse mod of b by a. So this is how you can write down modulus and argument of a complex number in different quadrants. And in case you want to write something called mod amplitude form of a complex number, mod amplitude form of a complex number. So we just have to express the complex number z equal to a plus ib in terms of r and theta, because usually r is the modulus and theta is the amplitude or argument. So whenever you have to write this from the same triangle, let us take the example of first quadrant. This is theta, this is r, a and b here, and I'm not writing mod because it is first quadrant. From this triangle, cos theta would be a by r. And this is suppose OMP triangle. From this I wrote cos theta, and from this sin theta is equal to b by r. So clearly you can replace a with r cos theta, b with r sin theta. So you can write this as r into cos theta plus I sin theta. So this type of representation is called modulus amplitude form. And whenever you are writing a complex number in this notation, that theta amplitude should lie between minus pi and plus pi. And minus pi and pi will be the same place, because if you measure like this, this is pi. The same thing you measure like this is minus pi. So you can put equal to in one case, that would be enough. So if I'm putting equal to here, then I can avoid here. So the argument should lie in the interval. So you can say r is mod z into cos of theta is amplitude of z or argument of z. Anything we can write. I'm writing amplitude here, but both are same only. Sine of amplitude z. This type of representation is called modulus amplitude form of a complex number. And the same thing is also called polar form, because the r and theta, whenever you have a point, fixed point like this, and you have a line like this, if you measure the distance of point from a fixed point, which is called as the pole, and this line is called initial line. So there is a coordinate system called polar coordinate system, where we don't take two axes like x and y. Instead, we take a point and a line, and we measure with reference to that. So with reference to this line, it makes an angle theta. And this point is at a distance of r from this. So we can write r theta and call it as polar coordinates. And the relation between them is a equal to r cos theta, b equal to r sin theta. Since you wrote in terms of r and theta, these are also called polar coordinates. That is why it is also called by the name polar form. And apart from this, we have one property called Euler's theorem. So e power I theta equal to cos theta plus I sin theta. This is called Euler's theorem. So the proof we can learn this in limits chapter. So because of this theorem, the complex number which you wrote as r into cos theta plus I sin theta, which was called mod amplitude form or polar form, can also be represented as r into e power I theta, and then you can call it as polar form of the complex number. This is called polar form. And writing a complex number in polar form will help you in multiplying and dividing them easily. Like for example, you have a complex number r1 e power I theta 1. Another complex number r2 e power I theta 2. So one more complex number r3 e power I theta 3, etc. So if you have to do something like z1, z2 divided by z3, so straight away you can multiply the modulus of these two, that is r1, r2. And when you multiply z1 and z2, powers will add, it becomes e power I theta 1 plus theta 2. Divided by z3 is r3 e power I theta 3. So r1, r2, r3 are numbers, they'll just get divided directly. And the powers of e will get subtracted in division. So you'll get e power I times theta 1 plus theta 2 minus theta 3. So that means for the new complex number which you got z1, z2 by z3, modulus is r1, r2 by r3. And what angle you have in the power is nothing but the argument of that. So you can say that is the argument. So this is also written in mod amplitude form. And whenever you have many complex numbers, division and multiplication becomes easier when you represent in polar form notation. That is in terms of powers of e, it would be easier. But only thing that you have to conclude is when you write the argument, you have to simplify this angle and check it should be in the form between minus pi to plus pi. So if it's not in the interval, what is to be done? I'll explain it later. But right now, so just as an application, you can see that we can do multiplication division easily using polar form. That's what we want to understand. We are not bothered about the limits of this angle right now, which we'll be discussing in the later part of the chapter. So I hope that was clear to all of you. Now, we'll be doing some problems based on this concept. The first question is, you have to find the amplitude of Z, given that Z satisfies this equation. So first we'll write Z value as, the right hand side will write as it is. The term which is multiplied to Z in the left hand side will divide in the right side. It will be 2 minus 2i root 3 whole square. So you can do it by converting this in mod amplitude form for each of the complex numbers. Otherwise, also we can just do normal calculation and convert in a plus ib form and find the argument. Okay, so I'll write I as it is. Root 3 plus I power 4, if I have to simplify, you can square double time. So when you square it for first time, it will become 3 plus I square plus 2i root 3 power 2. Because one squaring is done, one more square will remain. In the denominator, 2 is common. Squaring will give 4. And I have 1 minus I root 3 whole square, which is 1 plus 3i square minus 2i root 3. So I'm just expanding directly. So I into, now write this I square as minus 1. So you'll get 3 minus 1, 2 here, plus 2i root 3 whole square by 4 into this I square. When I write minus 1, we'll get 1 minus 3, that is minus 2 minus 2i root 3. Now in the numerator, if I take 2 common and square, we'll get 4. So you'll get 4i into, again, 1 plus I root 3 whole square. We'll simplify that again. By, in the denominator, if I take 4 is already there, I can actually take minus 2 also common. Then I'll have 1 plus I root 3 here. So this 4 will cancel. 1 plus I root 3 whole square and 1 plus I root 3 you can cancel, 4, and you'll have I by, so you'll get I into 1 plus I root 3 divided by minus 2, because this term already got cancelled. So only minus 2 would remain here. So that is minus half into, bring that I inside, it will become I into I plus I into I root 3 is I square root 3, because I square is minus 1, we'll get minus here. And when you open the brackets, it actually gives you root 3 by 2 minus I by 2. So this complex number is in which quadrant now? X, A positive, B negative would be fourth quadrant. And for fourth quadrant, what is the formula for the argument of Z? Minus tan inverse of mod of B by A. So you can write this as minus tan inverse of mod of B is minus half by A is root 3 by 2. So that will give you minus tan inverse 1 by root 3, because mod will make this positive. And tan inverse 1 by root 3 is 30 degrees. So pi by 6. So minus pi by 6 would be the right answer for this. So we can mark B option as the answer. So whether we say amplitude or argument, it is one and the same. So whether I use the word argument Z or amplitude of Z, it means the same thing only. So this was quite simple. Now let's move on to next question. You are given Z and you have to see which of the options is correct, where you need to know what is real part, imaginary part, and amplitude, etc. So whenever you want to find all these things, you have to again express the complex number in A plus IB form. For that, if there is a division of two complex numbers, we always have to remove the complex number in denominator, make it real, for which you need to multiply and divide by its conjugate. So multiply and divide by 1 minus I. In the denominator, 1 plus I into 1 minus I would become 1 minus I square. In the numerator, you do multiplication directly. That is 1 into 1 minus I will be 1 minus I. Then 3i into 1 is 3i. And then we have 3i into minus I is minus 3i square, which is minus 1, we'll get plus 3. So this would give you 3 plus 1, 4. 3i minus I is 2i divided by, in the denominator, if you put I square as minus 1, this will give you 2. So when you take 2 common and cancel, it gives you 2 plus I. So clearly you can see that the real part of the complex number is 2 here. And imaginary, this is 1i, so imaginary part of Z is 1. So real part of Z is 2 times imaginary part of Z. First option is correct anyway. And let us check. Second one is obviously not correct when first one holds. What is mod Z? Root of A square plus B square, 2 square plus 1 square, which is root 5. So actually for this, even C is also a correct option. And amplitude of Z, if I write down, it is tan inverse mod of B by A, tan inverse 1 by 2. If I give you, it is correct. But they gave tan inverse Z, which is not correct. So this is wrong and this is wrong. Only A and C are correct answers. So this is also quite simple. Now let's move on to the next question. We have to find out the possible value of I power I. So one of the values means you need not find general solution. Any one possible value you need to find out. So whenever you have I power I involved, you can write this in terms of e power of something. So we know that this I can be written as 0 plus 1i whole power I. And if I have to write in cos and sine, you know 0 is cos 90 1 is sine 90. I can write cos pi by 2 plus I sine pi by 2 whole power I. Then we know that cos theta plus I sine theta can be written as e power I theta. So write e power I pi by 2 whole power I. And on simplifying, this is e power I square pi by 2. Now writing I square as -1, it would reduce to e power minus pi by 2. So therefore, option B is the right answer for this. Even this is quite simple. Let's move on to the next question. So you are given the complex number ZR and you need to find a product like this. So first thing, ZR is cos r pi by 10 plus I sin r pi by 10. So it's in the form of cos theta plus I sin theta. In Euler's form, you can write e power I theta. Why I'm writing in Euler's form? Because it is usually easy to multiply and divide in Euler's form. That's why I wrote. So what does this represent? Basically, pi r equal to 1 to 4 ZR. Pi is a symbol for multiplication, just like sigma is for addition. So the meaning of this is when you put r as 1 to 4, all the values are supposed to multiply. That is the meaning of this. So our Z1 would be the same thing with r substitute as 1 e power I pi by 10. Z2 means you have to put r as 2 e power I 2 pi by 10. Z3 would be obtained by putting r as 3, Z4 by putting r as 4, and these are the values that you get. And since all are in powers of e, in multiplication powers will add. So e power I times, when you add pi by 10, 2 pi by 10, 3 pi by 10, 4 pi by 10, you will actually get 10 pi by 10. And cancelling out 10, it is same as e power I pi. And you know that e power I pi can be written as cos pi plus I sin pi. Since we know that cos pi is -1 and sin pi is 0, you'll get -1 plus I times of 0. So answer would be -1. So C is the right answer. Okay. Now let's move on to the next one. So we have to find out the value of tan of I log of a minus ib by a plus ib. So whenever you have logarithm of complex number, you always have to convert this in terms of power of e. So for that, you have to involve cos theta, sin theta. Then only you can convert in powers of e. Why? Because you know that e power I theta is cos theta plus I sin theta. So if you are getting this in cos and sin, you can convert in power of e, and logarithm of e power something base e can be simplified. So our idea would be to convert this in terms of cos and sin. So let us assume that a is some r cos theta and b is some r sin theta. Let us assume like this. So then you can write this as r cos theta minus I times r sin theta divided by r cos theta plus I times r sin theta. Now taking r common in the numerator and denominator, this would be r into cos theta minus I sin theta by r into cos theta plus I sin theta. So cancel out this r from here. And if you express it in power of e, this is e power I theta. And if there is a minus sign, it is e power minus I theta. So this would simplify to e power, subtraction of powers will give you minus 2I theta. And you wanted logarithm of this. So if you have to find the logarithm of this term to base e, the power when multiplies to logarithm, you'll get log e base e, which is 1. So this is minus 2I theta. And you wanted tan of I times of log of this. So that is tan of I times of this value means when you multiply with I, it will become minus 2I square, which will be plus 2. So tan 2 theta, which is 2 tan theta by 1 minus tan square theta using trigonometry formulas. And since you have assumed that A is r cos theta and B is r sin theta, so by dividing these two, we can see that tan theta is B by A. From here, you can see that B by A is tan theta. So putting tan theta as B by A here, this would be 2 times B by A divided by 1 minus B square by A square. On simplifying, this would reduce to 2AB by A square minus B square. Now let us look at the options. So clearly you can see that D option is the right answer for this. Okay.